So here's an example. One of the most common transformers you're going to encounter in a commercial and industrial building always start with a delta 13.8 on one side and with 482.77 in the other side. 99% of the bigger commercial buildings and industrial buildings start with this transformer. What Gary told you guys yesterday, but when he showed with the substation, what they do for a substation, I'm just going to draw that one. What they do for substation is, here's what a substation is. They divide it into 3 sections, and they put the transformer that you're looking at right now, they put it right in here, and then they put a disconnect and a fuse right in here, and they bust them together inside an overcap protection device and have a panel on that side. That's what a substation is. Oops. A substation is. And then they call this section high voltage, transformer, and low voltage. In this case, if you want to put this transformer here, that will be, the high voltage will be 13.8 K. This obviously, let's just say it was 1.5 kVA, and this transformer right here, this panel, let's just say it was a 3000 amp. All bust together. That's what a unit substation is. Why would they do something like this? Clean cut, beautiful. So you go to Mayo Clinic, guys, Ganda building, the 13th floor. They take a feeder coming from the basement of Mayo Clinic building, Ganda building. They take the feeder and they pull that feeder right through the building, medium voltage feeder, all the way to the 13th floor. All the way to the 13th floor. That feeder will land into a unit substation like this. And the unit substation into a disconnect fuse, feed a transformer, and this will be your 480 system. This will be your 480/277 system that feed all the chillers and the air handling units and all the mechanical equipment and lights and so forth. And then from here, from this switch here, they feed multiple things, as you might imagine. There will be multiple panels fed from this switch here, right? These are all, there will be lighting panel, mechanical panel 1, mechanical panel 2, there will be UPS. Does that make sense? All these will be fed directly from this low voltage section. They call it low voltage section. That's what they're in substation. So why did I pick this one? Because this transformer fits directly into the that page. So this transformer that you're looking at right now can fit right into this box, okay? Any question, guys, how these are tied into the UPS system, into the unit substation? Any question? Okay, so the question would be is we're going to go size the fuse. Can you guys see the fuse here? We need to size the fuse on the primary, and we need to size the fuse in the secondary and the cables. That's why we have this example. So let's go ahead and size the fuse. Some of this information you guys already know. So let me erase this and start with a couple of calculations that we need to do. All right, so let's use blue here, color blue. Okay, so what do we have? We have a transformer on the primary. It's connected 3-phase. On the secondary, guys, instead of having one big fat transformer, they call it bank of transformers. There's 3 ways of getting 3-phase system. The best way is to have one big transformer 3-phase. They call it big 3-phase transformer. The second way is to have 3 single transformers like these, 3 single transformers. Here's the 3 single transformers, and they hook them up. They hook them up in delta in one side, and they hook them up in a Y in another side. So what you're looking at right now is these are 3 single-phase transformer barrels. Each one of them is 75 kVA. Cool? And they are hooked up to make a 3-phase system. That's one way of making 3-phase systems. This is not what we do in a commercial building. Typically in a commercial building, guys, instead of 3 pieces, all these will be in one big fat transformer. Cool? The calculation wouldn't be, when we do all the calculation that we're going to do, guys, it's the same. If they are 1 or one big box or three little boxes. Cool. So let's go ahead and do the calculation for this system, if you don't mind. Okay, so this is phase C. So let's look at what we have. We have a delta Y transformer. On the primary side, we have phase A, B, C. We have 13.8 kV with the fuses. On the secondary side, we have a Y, center tab, Z in the middle is the impedance of this transformer. It will help us calculate the short circuit. On the secondary side, we need the fuses. We need to size the fuses as well as the circuit breakers, the fuses as well as the feeders. The secondary is 480. Each one of these three transformers is 75 kV. Any question about what we have? Any question about what we have? Three transformers, each one of them is 75. On the primary side, they're hooked up 13.8. On the secondary side, they're hooked up Y 482.77. Cool? Okay, so the first question, guys, would be as they call it, because they bank them, they call it banked kVA. So please let me know if you want me to read some of my handwriting for you. This is called banked because they're banked together, kVA. The reason why they call it banked kVA because there's three of them. When you bank them together, what do you do for the kVA? How many of them do I have? I have three of them, so it becomes 3 times what? 3 times 75 kVA. And my friends, this will get you a healthy 225 kVA bank. So these three together equivalent to 225 kVA. Cool? That makes sense? So for all practical reasons, I can go get rid of them and buy a 225 kVA transformer and stick that transformer right there, and the outcome is completely the same. Therein, my friend, when you have a three-phase transformer, that's what you have. You have 225 kVA. You don't have the 75. Cool? Okay, the second thing I would like you guys to do, there is voltage phase, voltage primary line. This is P for primary, L for line, and this is voltage primary coil. So the voltage, we know what you guys are familiar with the transformers. There's a coil voltage. The coil voltage is right across the coil. That's called coil voltage. The line voltage is right across two lines. Cool? Everybody understand what a coil voltage and a phase voltage, a coil voltage or phase voltage and a line voltage? P for primary, L for line, P for primary, C for coil. Okay, in a delta, the coil voltage and the line voltage are what? Identical, right? Look at the voltage. You take the voltmeter, measure from here or measure from here. Would you get the same thing? Yeah, you get 13.8. So what's the coil voltage for this system? This baby is 13.8 kV. Here's the coil voltage. This is the line voltage. What's the coil voltage? Identical, right? Same thing. 13.8 kV. 13.8 kV. Any question, guys, about the coil voltage and the line voltage? The coil voltage and the line voltage. And I know this is not a new concept for you, the coil voltage and the line voltage. Okay, so here's my coil voltage, my line voltage. This is on the primary side. On the secondary side, the same thing. On the secondary side, the line voltage is between the neutral and phase A, the neutral, phase B, the neutral, and phase C. So if you guys go between phase A and the neutral, what do you get? Phase A and the neutral. That will be secondary, no, that's secondary line. If you go between phase A and phase B line-wise, what do you get? 480, right? So this is my 480. Any question, guys, about the line voltage and the coil or the phase voltage? The line voltage and the coil or the phase voltage. Do me a favor, right next to the line voltage, put a star. This is the voltage that we use for all our calculations. The line voltage. We don't care about the coil voltage. Coil voltage is, for calculation-wise, it's just in the back of your mind, but we really care about the line voltage, the one that we use all the time in the calculation. So I put a star next to it because that's the most important quantity you're going to have, the line voltage. There's line voltage on the primary, line voltage in the secondary, coil voltage on the primary, coil voltage on the secondary. Any question, guys? And I know some of these are repetitive, so just a quick review, or a line and a coil voltage, or a phase voltage. Okay, questions, move on to next. Okay, so let's go to the next one. The next one, just identification. Oops, I think I misspoke, and this looks like a C. I think I meant one of them. What did we? Okay, so let's make the secondary line. Let's just make this as a line. Well, if you guys make this is V, secondary L. This looks like a line here. V secondary line. Can you guys change that one? V secondary line. Let's do this one. V secondary coil. V secondary coil. I will erase that one. Make this is V second. Doesn't matter which one of them you do first. V secondary coil. Okay. Looks like a coil. Secondary coil. Okay. So for the secondary coil, what's the voltage line to neutral? 277. So this one is piece of cake. 277 volt. 277 volt. Any comments, guys? Any questions about this? Any comments? Any questions? Okay. Why did I jump to 4? What happened to 5? Is yours guys show the 5? No. Okay. Let's just make him 5, will you? I don't know why I jumped to. I think I was drunk, probably.
Well, line 6 says IPL. We're off there. 7 is I, secondary current.
Line 6, we're off by.
Line 6 is different.
Did it? Okay. What does your line 6 say?
IPL.
Which you don't have up there.
Yeah.
So VCS should have been 5.
No, I hear you. I think the file is. That's the file that I printed for you guys, though. Why it's not? Okay, give me a second here. Extend page. No, there's nothing here. Interesting. Okay, well, really doesn't matter. We can make them, but I want to follow what you guys have. So, what do you have for up to this? Is this 4 for you?
Yeah.
Okay. So, what does 5 say?
You don't have 5.
You don't have 5. Okay. I jumped into. Okay, we don't have 5. Okay, so let's do it this way. Let's make it easy. Let's make this one 5, and then I put I. Let's make this one 5, will you? Just do me a favor. So let's do 5 here. This will be my 5, and this will be the secondary coil, okay? And I'm gonna make this as 6, and that will be just to start with I primary line. Cool? Can you guys do a little adjustment? Just add a 5. Now we're back on track. Back on track. Okay, I primary line. You guys have I primary line, right? I primary line. Just a little adjustment. I primary line. So we have 2 pieces of cake. So the primary line, you take 225K divided by the. Remember, we're talking about the primary. So it's a 3-phase, 1.73 times the 13.8K. 13.8K. 13.8K, right? Now, since there is a K at the top and a K at the bottom, you know what you do with the K? It's just the 2 Ks go together to make the calculation easier, right? or you can put the K. If there's K at the top and K at the bottom, the easiest way to cancel the K's together. And that will get you, please check that one for me. It gets you 9.4 amps. 9.4 amps. Anybody did the math? 9.4 amps. 9.4 amps. So this is my I primary line. I primary line. And the I primary line, do me a favor, could you please put a star next to it? Because that's important when we start sizing the conductors. We always size based on the line voltage and the line current. Line voltage, line current. Cool? I secondary line, same thing. Let's go to I secondary line. The same 225K. Divide this one by 1.73 times 480, right? Times 480. Right? This is the formula that we use. And you guys are familiar, we take the KVA divided by the voltage and you put the multiplier for the three phase. This one equal 271 amp. 271 amp. Can you please verify that one? 271 amp. So we found the primary and the secondary amps, basically. Primary and secondary amps. Okay, so primary and secondary amps. The reason why I put a star, a red star next to them, because this is what we size the feeders and the fuses based on the line current and the line voltage, not the coil, not the coil. The coil is FYI only. Okay, let's go to the I primary coil. I primary coil, I just want to remind you guys, if you go to the diagram, it is a delta. In a delta, the I line right in here. This is my I primary line. I primary coil, this is I primary coil right in here. And the coil is always the line divided by 1.73 in a delta. If you guys remember the rules of a delta, since it's a delta, since it's a delta, I'm going to put the rule here, I primary coil, since it's a delta, equal I primary line divided by 1.73 or 9.4 divided by 1.73, and that will get you a healthy 5.4 amps. Okay, in a delta the line current is bigger than the coil current in a delta. In a Y guys, they're the same. Okay, everybody can see that the current that's coming out of here is the same current that's coming out of the coil, right? This is the coil, this is the line. Both of them are the same in a Y. And I'm moving fast on these because you guys know these rules. So this is I secondary coil equal I secondary line. And what's the I secondary line? 271 amps. Done. The reason, Andrew, that I did not highlight the 8 and the 9, but did not put star next to them, because they're FYI only. Really they don't do anything in the calculation. Anything that has a star next to it is the one they're going to use to size the fuses and the circuit breakers on the primary if it's a primary side, or on the secondary if it's a secondary side. Any questions about this? Some of it is repetitive, right? Catching up a little bit. Okay. Now that's what you did with Gary yesterday when he talked about unit substation. That's what we basically find the transformer. We're just looking at the transformer. Jeff, are the calculation right? The numbers? Okay. All right, should I move to 10? 10, okay. 10, transformer ratio. Transformer ratio, guys, is defined as, these are FYI only, well, we use it a little bit. Transformer ratio is always defined as V, the voltage. My V is my voltage. V primary coil divided by V secondary coil. Coil to coil. The voltage in the coil divided by the voltage in the coil, primary and secondary. Okay, that's piece of cake. You take 13.8K, divide this baby by 200, 277. Remember, it's coil to coil. That will get you 50. And from here, the ratio is 50 to 1, right? Now how we write the ratio? 50 to 1. For every 50 volt on the primary, there is a 1 volt on the secondary. That's what this is telling you. Coil to coil. For every,
The line is 480, the coil.
Yeah. yeah, there are two, yeah, there are two transformer ratios. One line to line and one coil to coil. The transformer ratio is defined as coil to coil. The transformation, this is supposed to be transformation ratio, exactly what you said. This would be V primary line divided by V primary coil. They call it transformation ratio. This is 13A, stays the same. This one, 470, right? I mean 480. And if you guys did that one, but did that give me 29, and that will transfer into 29 to 1. Now, what does each one of these mean? What does each one of them mean? Means the primary line voltage is 29 times more than the secondary line voltage. Does that make sense? This one means the primary coil voltage is 50 times more than the secondary coil voltage. Does that make sense? The coil versus the line. This value is the one that they use to find a lot of transformation. We don't use it a lot in what we apply yet, but this is the value that can get you voltage to voltage, primary to primary. Any question, guys? Any comments about this? Any questions? Okay, so now all this is FYI. Now we're going to start sizing. We do transformers, guys, because we need to size the primary and secondary transformer. So primary feeder size. Now, here's where the assumption that we're going to do. We have to make an assumption. When we size the transformer, do you have a continuous load coming out of the transformer or not? That's a major assumption. What do you do if you have a continuous load, Jeff?
Isn't that the secondary coil?
V primary should be line. Sorry, thank you. Should be an L.
You're dividing it by itself. Yeah, you're dividing it by itself. Shouldn't it be the V secondary coil?
So V primary line divided by V secondary line. Thank you. Yep. V secondary line. Thank you. I just wrote it wrong. Thank you. V secondary line. Good. Okay. Any question? Thank you. Any question, guys, about this before we move into sizing the feeders? Primary feeder. The primary feeder, guys, when we size a primary feeder, we always size based on I primary line. What's the I primary line? We just got the I primary line a second ago. That was 9.4. 9.4 N. 9.4 N. I want to remind you guys, this is also at 13,800 kV. These amps are at 13,800 kV. So when we size the conductor, can I size a 600 volt conductor? No, doesn't get you there. So I have to go size a conductor that's based on 13,800 kV. Okay, so how do we do that? The second assumption that we're going to do before we do that. So this is the first assumption. Second thing is, I'm going to assume it's continuous load. What do you do if it's continuous load? 1.25. So I'm going to take the 1.25. I did not do the math, so I need somebody to help me with this, please. Equal. What's 1.25 times 9.4? Anybody? I need two gentlemen to agree on that. How much? 11.75. 11.8 is good. M. 11.8 M. Okay? Why? Some people, guys, don't even multiply. You're going to see it doesn't even make a difference here when we size the cable. Does it really make a difference? The second thing you need to do, so the third thing, is you're going to take the 11.8 K M. Now we're going to take this one to one table. This table, I think we used it last time too. 310 dot. Okay, so let's go to 310 dot 60. I know the changes since I dot 60 something. 77. It should be 310 dot 77, but dot 60 now, right? 310 dot 60 C77. Thank you. This should be 310 dot 6. Oops. 310 dot 60. 310 dot 60 C77. NEC 2011. Okay? If you guys go there, I'm going to do it one time, and then I'll give me a second here. Go quick. We'll do it one time. So let me just go very quick here and come from the back. Okay, here's the table 310.77 all the way. Did we say 310.77, right? 310, yeah. Okay, 79, 77. Here you go, this one. So when you go to 310, let's just read about this table. This is the ambiguity of three single insulated conductors covered in underground electrical ducts. 3 conductors per electrical duct based on an ambient temperature of this. So this is for cover conductor, 3 conductors in a conduit. That's perfect. We're coming from underground in a duct. So that matches what we do. That's why we use this one. So do me a favor, guys. Highlight this table. I know we used it before. Then, how many circuits do we have? One circuit. For what? How many circuits do we have? We have only one circuit. Are we paralleling? We're not paralleling. We only have one circuit. So first we use this one because it's single conductor and it's copper because we want to use copper. Then the second thing you need to pay attention to is that it's one circuit. Then what's the voltage? 13.8. So 13.8, is it here or here? I have a 13.8 K voltage, so I am right in here, right? Everybody understand why I went to this column, right? So that's why I went to this column. Now, which insulation am I going to be using? 90 or 105? If you don't know, it's like 75 and 90. Remember that 75 and 90, you always go 90 unless you know otherwise. So default is what? 90. So I'm going to go to 90. So now I'm right in here. Okay, let's go size. What's the smallest conductor that you can get here? It gives you how many amps? 90 amps. How much amp do I need? 11 point. So see how it didn't make even a difference in the whole calculation that we did because medium voltage. So what's the size? That's the smallest they can buy at this voltage. What's the size? Number 6. Any question, guys, about this? See how easy that is? That's the table that we use for high voltage. Okay. I'm going to take a snapshot at it. Okay. And then go back. Okay, so here's, everybody highlighted it. I took a snapshot. This will be PDF for you. Now, if you're Carrie, my friend, if your homework is 4160 voltage, you're going to be where? Right in this column. Okay, so everybody understand why we came up with number 6? So now let's go back and get our number 6 here. So this will be, how many conductors though? How are we going to write this one? This will be 3 conductors. Why 3 conductors? 3 phase. Do I need a neutral in the primary? No neutral. 3 conductors. Number 6 AWG, and what's the insulation? MV-90. That's, huh?
Okay.
Did they do it right? We use the 90, right?
You're using that here.
Yeah, default is 90. Your default is 90. So gentlemen, here's your size of your conductor. That's the size of your conductor. Any question, guys? See how even a 1.25 there did not make a difference on the primary side. Okay. Any question, guys, about this table? I have it here as a PDF here. Any question about this table? Why this table? This is the most commonly used table because when we have medium voltage, where do we come from? Underground. If you did not come from underground, then you have to use other tables, which we will be using. That's not underground cables. Most of these tables, guys, are for underground because if you have medium voltage, typically they're coming from to a building, not to the transmission line coming from underground. Okay, can I move to the next one, guys? May I move to the next one? So that's number 12. Let's go to number 13. Number 13 is secondary conductors. And I also need help with this one, please. Number 13 is secondary conductors. Secondary conductors, we size it based on 271 amps. You always size based on the line current. Always. The line current. Always. Not the coil current. So 271. Okay? So that's my my conductor size, number 13. Then, what do I need to do? Now, here's where an assumption that you have to do. Are we going to make it a continuous load? Are we going to assume it's continuous load? That's an assumption.
Where'd you get 271?
271 from the I secondary line. No?
Okay.
Yeah? Is it? Did I?
This is here where you said it.
Yeah, I secondary line. Because we are on the secondary side, on the line side. I secondary line. Am I going too fast, guys?
No, I don't.
No?
Use your LFSC.
Okay. I secondary line. This is an, I know this is a hard one. This is S, L. Is that good, L? Okay. That's as good as it could. Secondary line. Okay. The second thing, guys, I want to assume it's continuous load, so 1.25. I need somebody to do this one, please. 271 amps. Can somebody do the math for me, please?
338. Or it's actually 339.
339. Do I have a second? Okay. And the third thing that you need to do here is to take your 339 amp. Now, which table? This is very familiar with the table 310.15B16. That's very easy. Which column and why? Under column 75 degree column Celsius. 75 degree. Why 75? Thank you. 75. I want to do it one time. I know we've done it one time. Okay, so let's go one more time for these. And did you guys get 500? Okay, so let's go to this baby. I'm going to erase this. Based on what Andrew told me to do when you do them. Okay, here's the table that we're going to highlight, guys. 310 to 16. And what was the amps that we're looking for? 300? 339. 339, that will give me 500. Everybody can see that? So do me a favor. Highlight this table. Come on. Highlight this table. If you haven't done it before, this is the most common table you're going to be using. Why did we go to 75? Because we are more than 100. Here's my amps, and here's my size, 500. Cool? Any question, guys, about why did I use this side, not the other side? We're copper oriented. If you and if your company uses aluminum, you're going to be sizing based on this side, on the right side. Any question, guys, about this? So 500. How many 500s? 3, but 3 phases. Are we going to pull a full neutral or not? We'll talk about this one in a second. So let me take a snapshot of that. Did we do a snapshot? No, we didn't do a snapshot. Doesn't want to do a snapshot. Okay. Um, should do it. No, 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 no. Let's go. So let's go size it. I'm gonna go then right in here. I'm gonna go now. Here's the rules that you guys gonna do. Up to 300 amp, probably I would 300, 400 full neutral because your receptacle panels. Higher than that one, we start derating the neutral. I'll show you later on a bigger example. So for this time, I decided to use full neutral. That's a decision that you have made. So I'm gonna go over here and take how many conductors? Right in here, underneath it. I want to say 4 conductors, number 500 kcm. What type of insulation? Let's just say we are inside the building, THHN. Could I have pulled 3 conductors and no neutral because I don't use a neutral in the building? Yes. Could I have pulled lower and neutral if I did a neutral calculation? Yes. Cool. So we decided to put full neutral for this one. 4 conductor, 500 kcm. Okay, shall we do the fuse? Let's do the fuse. Primary overcam protection device fuse. For the primary overcam protection device fuse, guys, for the primary overcam protection device fuse, here's the table that we're going to go to. If you write to yourself a note, table 450.3a. 3a. 450.3a. From 450.3a, because it's a transformer, here's what it tells me. It says the multiplier has to be 3. You multiply it always by I primary line. And if you do the math on that one, that will be 3 times 9.4. And that will get you 3 times 9.4 is 28 amps. Then you take the 28 amps. We take this one to 240.6. You guys remember that? 240.6. And if it's not a standard, you go to the next standard, which is 30 amps. If it's not a standard, you have to go up. If it's not a standard, you have to go up. Go up if it's not a standard. So what size fuse do I have on the primary side? 30 amps. What size fuse do I have on the primary side? 30 amps. On the secondary side, the same table. If you go to the same table, table 430.3a. Did I get my milk today? 450.3a. Same table. Okay. On the secondary side, guys, I'm going to show you the multiplier that we'll be using. The multiplier is 1.25. Multiply this baby, 1.25 by I secondary line. The line equal 1.25 times, what's the I secondary line? 271 amp. And that will give me a healthy 339 amps. We did that calculation before, right? Okay, next step is to take the 339 amp, take this one to 240.6. Everybody have been there? What's the next standard? Do we have 450? 350. Yep, we have 350. So 350 amp. 350 amp. Now, Aaron, how many fuses do I need? 3. On the primary, 3. On the secondary, 3. Do we fuse the neutral? No. fuses only the ungrounded conductor. We do not fuse in neutral. I'll give you guys a break in a second here. 1 second, hold your horses with me. I want to do the short circuit. Any question, guys, about this? Any question? Yes, sir.
For the secondary OCPD, don't you use table 450 to 3B?
Good point. Let's go there. Give me 1 second here. Let's go there and see why did we use this table. Let's go to the transformer. 450. Here's my 4, and here's my 50. You guys probably ahead of me with my. Okay. Okay. Let's go to the tables. The first thing, let me erase that one. I should have done that one here. Okay. The first table, guys, A, it says maximum rating sitting over connection device over 600 volt as a percentage of transformer. In the transformer, if the primary or the secondary or both more than 600 volt, you use A. B, if both the primary and the secondary are 600 volt. Can you guys write yourself a note? B is if both the primary and the secondary, both are less than 600 volt or less. If one of them is more than 600 volt, you have to go to the A. Okay, so if you look at A, here's a table that you can do because we have two voltages here. We have 13.8K on one side and 480 volt on the other side. So let's do the first, when you use this one, because the primary, guys, is here's the primary, right? This is my voltage, so you're going to go to the over 600 volt. Am I using a fuse or circuit breaker? Typically, we use a fuse cheaper. Any location, because I have no idea where I am. And what's my multiplier? What's my multiplier? 300. See what 300? Why did I go up? If you guys read note number 1, it tells you if you did not hit a standard, what do? We go up. And I know we covered this one before, but it's good to go over it one more time. Cool? Now, on the secondary side, though, look, let's do the secondary. On the secondary, what's the voltage? 480. So am I over 600 volt on the secondary? No. Here's my secondary. I am 600 volt or less. It doesn't matter if you use a fuse or circuit breaker. What's your multiplier? Oh, by the way, the impedance, no more than 6. What was the impedance that I gave you for that boy? I said 6. No more than 6, right? So that's right there. So I use this impedance because it's 6. And here's my multiplier. Do I also have note number 1? Yep. So we have to use note number 1. Any question, guys, about how to use this table? So that's where your table is. No, you go down here. More than 6. More than 10? Then then you have to follow the manufacturer's instructions. Typically, more than 10 is high impedance. You know what a high impedance means? You have voltage drop problem and losses, you know. So these are typical values. If you have different than that for whatever application they use, then you have to follow you have different rules. Any question, guys, about this table? Very good point. Okay. So we got that one. We got the 350 fuses. The last thing I want to do, guys, is a short circuit. Before I get you the homework, okay, here's my short circuit. The short circuit is always defined. Always in the secondary. Short circuit always in the secondary. Secondary line short. This is how I'm going to say instead of SC that will confuse you with coil, guys. I'm going to say short circuit. Short. Can you guys change this one to I short circuit? I short circuit equal I secondary line divided by Z impedance. The impedance. What was the secondary line? 271. Divide this. What was the impedance? 6%. That will become 0.06, and that will get you a healthy. Is this 45K or 4.5K? Can somebody that does that for me? Divide the 271 by 0.06. 4.5K. 4.5K kiloamp. What does that mean? Means the circuit breaker inside this panel that's going to be tied to this transformer, they have to be rated for 4.5K or higher. Or higher. This one, let me change the impedance. This is a 2% impedance. Your homework, my friend, is here's a 2%. Your homework is right in here. Homework number 1. You have your primary is 4160. Your secondary is 28120. Your transformer KVA, pure transformer. Did you guys hear pure transformer? So the total one is what? If we have 3 transformers, if each one of them is 100, the total is 300. 300, the impedance, this is Z, believe it or not. My Z. Should I put like Z? This. Here's my Z or Z, 20%. 2%. This is not
You said 20.
Yeah, thank you. 2%. 20, that would be a big impedance. Any question, guys? So that's the homework for this one. I'm gonna give you 5 minutes and hit the second one. Thank you. It's a delta Y, the same thing. Very good point. Let me clarify it. This is a delta side. This is a Y grounded side. Delta Y. Delta Y. Cool. And what do you need to do, guys? Do the same steps. That 16 steps. 16 steps. That'll get you some exercise in it. 5 minutes. Okay, let's go ahead, guys, if you don't mind me here. Okay, so everybody got the homework? Cool. Let's go to the next example. Here's the next example, identical. I'm going to go a little bit faster on this one. It's a transformer. This time is 480-277, 28120. The reason why I picked this transformer for you guys, because that's a typical transformer for receptacle panels in the US here. So I have 480 on the primary. On the secondary, I have 208. Here's the line voltage. Coil voltage is shown. This is how we wire it. H1, H2, X1, X2. So in the secondary side, there are 3 transformers, 50 kVA each. Everybody can see that? 3 transformers, 50 kVA each. On the primary side, they are wired delta. On the secondary side, they are wired Y. H's are on the primary. X's are on the secondary. We put all the X1s timed together, connected to Mother Earth, to the ground. That should get neutral. X2, we took the phases from it. For the delta, we brought every X1 to H1 to H2, H1 to H2, and we brought a phase in between them. Before I move away from this picture, anybody has any question about this? So what's my goal? My goal is to do 2 things. Size the primary fuses and feeders, secondary fuses and feeders. Cool? We're going to repeat everything that we did. The only difference for this one, guys, do you see what the voltage on the primary is? 480. There's no high voltage in the primary. Okay? Should we go ahead and start? Piece of cake? Yes? No? Anybody? Any question about that one? There are still 3 transformers. Okay, so let's go ahead and do the bank. So 3 transformers. Banked KVA. What's the banked KVA for these transformers? The banked KVA, guys, is 3 times 50 K. Everybody knows why 3 times 50 equal 150 kVA. Piece of cake. Now I'm moving a little bit faster on these because 3 times 50 is 150. Everybody knows why 3? Because there's 3 of them. Primary line voltage. Primary line voltage is, what's the line voltage in the primary? 480 volt. Piece of cake. Primary coil voltage. Primary coil voltage equal V primary coil equal V primary line equal 480. Why is it 480, Jeff, my friend? because on the primary we are having a delta. We're having a delta on the primary, right? That's piece of cake. Secondary line voltage. Secondary line voltage, you guys look at it, it's a 208 volt. That's just looking at it. Secondary coil voltage equal 120 volt. I know I moved very, very fast through these. These are piece of cake. Really, just fill information. Any questions about this? That's not a whole lot. Just very fast, very quick. Just being able to collect this info and put them in. Can I move to 6, please? May I? Yes, no? Am I going too fast, Jeff, on that one? No? That's just picking information, right? Okay, number 6, primary line current. Everything does repeat itself here. Primary line current, when we do primary line current, you take, like we said, kVA divided by 1.73 times, what's the primary? Voltage, primary line. This will be 150 K divided by 1.73 times 480. And if you do the math on this, do I have 180? 180 amp. Can anybody verify it, please? Sometimes, a lot of times, they do mistakes. So please verify that one. On the secondary side, no difference. kVA divided by 1.73 times the V secondary line. You plug in the numbers, 150K divided by 1.73 times 208 equal, on the secondary side, I have 417 amps. Could anybody verify that one? 417 amps. 417 amps. Kiri, make sense? Okay, I wrote the formulas here for you. Primary coil current, do you guys remember the primary is a delta? The coil current is the prime, if it's a delta, it's less than the line current. So you take the line and divide it by what? 1.73. So if you take the coil here, equal I primary line divided by 1.73 equal piece of cake. Where's my line? Is 180. Divide this by 1.73 square root of 3. And that will get me I primary line, get me 108, 104. Can you guys verify that one? 104. Secondary coil current, piece of cake. I secondary coil equal I secondary line equal I secondary line is 417 amps. They're identical. Please have a star next to 6 and 7 because these are what we're going to be sizing based on. We size based on the line current, not the line current, not the coil current. Did I go too fast on that one, guys? I'll give you some time to write it, but really straightforward, Joe? No? Straightforward. I thought one more example plus the homework that you guys do, then we seal it. Done. Any question, guys, about this? Any question? Let me know when I can go to 10.
In your homework number 1, it says 100 kVA per transformer. That's supposed to be per phase.
Per transformer. It is actually, every transformer is a phase.
Okay.
Yeah, every transformer is a phase. If you have 3 single phase transformers, every transformer is really make a phase. Yeah. So long story short, you multiply them by 3. Yeah. Should we go to 10? Anybody? Yes? No, Darren? Yes, Aaron, am I? He was talking about the homework. The homework is 100 each. Okay, transformer ratio. A transformer ratio, guys, do you remember what the transformer ratio was? Transformer ratio was V primary coil over V secondary coil. And if you do this, it'll give you 480 divided by 120. That will give you 4. And this will give you a 4 to 1. Right? V primary coil over coil. Coil over coil. 480 divided by 120. Transformation is defined as V primary line over V secondary line. And that will give you 480 divided by 208. That will get you a healthy 2.3. And if you do it as a ratio, it becomes 2.3 to 1. 2.3 to 1. 2.3 to 1. Right? Piece of cake. I need you guys to help me with the primary feeder though, because I changed it here. 10 and 11 are piece of cake, right? You just have to remember which one of them is coil over coil, which one of them is line over line, right? Number 12. Number 12 is primary feeder size. We need the feeder size. Okay, here's what we need to do for feeder size. I need to do the following. We have to size it based on I primary line equal 180 amps. So Jeff, can you help me please with this? I need to assume it's continuous load, so I want to multiply it by 1.25 times, I did not do this, 80, an assumption. What would you get? How much?
225.
225 amp, thank you. And then the last step is you're going to take the 225 amp, you're going to take it to 310.15 B16. Remember that table under 75-degree column? I need gentlemen to go there and size it for me, please. How many conductors first? It's going to be 3 conductors. Each one of them is what? Anybody? Any second? Let's do Forat. A, W, G, T, H, H, N. Cool? Anybody second for the Forat? 225 is Forat. Why 3? There's a delta on the primary. There's no neutral, right? That's 3 conductors. On Andrew, my friend, on a test, I would like you guys, when you write it, to do the following. Number 1, the size. Number 2, the number. Number 3, the insulation. THHN. Unless I tell you it's going underground, you assume it's THHN. If it's underground, THHW.
What is the 1.25
1.25
Times 180.
A180, thank you, times, hate the writing on that one, and with my bad handwriting, 1.25 times. Is that times? 1.25 times 180. Why 1.25 continuous load? Right. Okay, let's do the secondary, will ya? On the secondary side, guys, on the secondary side, I'm going to do the same thing. I need to size I secondary line. Where was the I secondary line, gentlemen? Number 13 is I secondary line is 417. 41, oops, this should be 417 amps. I need to multiply this one by 1.25 times 417. I need somebody to help me with this. I don't have the answer for this. Four, 1, 7. How much? 521 amps. Any second? 521 amps. The last step is to take this number, guys, which is 521. Take it to table 310.15 B16. Can you read that even? And that will get you what size? How many conductors? I'm going to have full neutral. I'm not going to rate the neutral for the time being. I don't want to go through the rating of neutral. So how many conductors? I'm going to have 4 conductors. Are you paralleling? Okay. Shall we not parallel? Let's just not parallel now. Let's pull him. Let's not parallel. You can parallel. Just one set. 4 conductors number. How much? 900. 900 kcm T H H N. Okay. So basically 900 kcm. Should I parallel? Yes. Cut it by 2. If you parallel, you cut it by 2, and you end up with what? What's 2 sets of 300 kcm? Okay. Let me know when you guys can move to the fuses. Cool.
If you parallel, do you end up putting 6 fuses or could you still using 3 fuses before you?
3 fuses. Good point. When you parallel, good point. What happens if I parallel? Here's how they do it. Here's my fuse here, and here's my fuse holder from both sides, and then your conductors will be landing here. But the fuse still one fuse. Good point. Okay, the second step, guys, is to go. I need to find the fuses. Both of them are low voltage, so I'm going to go to table. Both of these baby are low voltage. So if you guys remember, I have to go to this table this time because both of them are low voltage. Okay, so here's my transformer. My transformer, 480, 208/120. This is the table that I need. Let's see, it's primary and secondary protection. Oh, oops, the default is primary and secondary protection right here. The primary is less than 9 amps, no current of 9 amps or more, right? That's primary. Here's my multiplier for the primary, and what's my multiplier for the secondary? Here's my secondary, current of 9 amps or more, and here's my multiplier for the secondary. I do have not number 1 and not number 1 go out. Okay? Everybody understand? Always default to the second, both protection primary and secondary. We have the current in the primary was more than 9, right? And on the secondary more than 9. And I'm using 1.25 here and 250. Can I go up on the primary? Does it say go up on the primary? Does it have note number 1? No, so you have to go down. If you read note number 3, guys, does it tell you to go up? Okay, so that's if you want to just write yourself a note here. Okay, so now that we have sorted that out. So primary overcome protection device for number 14. Here's what you're going to do. I'm going to use, always use I primary line, which is in this case was 180 amps. So what you do, then you take, we're doing the primary, right? Primary is 2.5 multiplied by 180. That will give me a healthy 2 primary line multiplied by 2.5. What do you get? What do you guys get? 450. I got 450. 450 amp. Then, right? Did I get different number? Take 450 amp. Take this one to 240.6, and what would that give you? What would that give you? 450. Do I have to go up or down first? So this is actually the same size, 450 amp. If it's not a standard, could you please write yourself a note here that you have to go down? If it's not a standard, what do? You go down. In this case, 450 is a standard. So we don't have to go up or down. But if it was 430, you're going to go to 400, not 450.
Is that for both A and B tables?
They're different in A and B. I believe in A you go up. You have to look at the table. Always look for note number 1. Does it have note number 1? Yup, you go up. It doesn't have note number 1, you go down. Okay, on the secondary side, guys, my friends, on the secondary side, we're going to use the same table, of course, on the secondary side here, which is table 450.3b. The current that I have, I secondary line was 417 amps. Then what do I need to do? I need to multiply this one by, what's my multiplier? We said 1.25. 1.25 times 417. This will give you a healthy 521 amps. And the last step, my friends, the last step is you take 521 amp, take it to 240.6. That will give you a healthy 600 amp. And if it's not a standard, what do? You go up. Okay? And here's the size of my fuses. How many fuses, Aaron? How many fuses? 3 fuses. Zach? One per phase. Yes,
So I need 3 600 fuses if you parallel?
no, it will be, if you parallel, you put the fuse, here's my fuse. Here's the fuse holder on both sides, right? You have to hold there. What they do is they have two lugs. One lug for one set and another lug for the other set from this side. From this side, it's tied to the transformer, right? Remember, this is the transformer side. This is what you put your 2 sets. Now, if you're paralleling 3, they will have 3 lugs tied to the same fuse. Make sense? Okay.
So why did we go up from the standard on the secondary? Is it because of the secondary or
Oh, why did we go up on the secondary and down on the primary?
yeah.
It's better protection.
So on the secondary you always go up or you go
Based on the table, yep. You don't have to. Remember, you can. There's a difference between you don't have to. So could have, by the way, I want you to go up based on the code, but I have 521. Could I have gone to 500 here? Yeah. Going up is a permission. You don't have to. As a matter of fact, a lot of engineers, when they do the short circuit calculation coordination, guys, they don't go up. But you have to prove why you didn't go up. You have to have some selectivity and coordination. The last thing is short circuit. The available short circuit. The available short circuit, and I want you guys to write it this way. I short circuit, which is right here, equal I secondary line over Z impedance. And do me a favor, what was the secondary line? 470, 417 divided, what was the impedance of that boy? Was it 0.5? Which is 0.05, 5%. And that will give me a healthy 8.3 kiloamps. So if this is a receptacle panel, guys, guess what's going to happen? I can get away with 10,000 amp fuses and circuit breakers. Why? Because the available short circuit is 8.3. All I have to do is just cover the available short circuit. 8.3, the next standard is 10 anyway. I don't have to go to 60,000 or so forth. Or so forth. Any questions about this? The last example. Any question, let me know, guys, when you're done so we can do the last example. Cool? Everybody's good? Okay, let's do this one. I want you guys to wake up a little bit. This guy So we have three examples. Two of them are delta Y. This one is delta delta center tap. This is you don't face it a lot, but you need to know how to use it. Delta 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 center tap. So let's look at this boy. This is a 2400 primary and a 240 123 phase secondary. That's the only way you can get a 240 123 phase secondary, by the way. It's the only way you can get 240 120 secondary is having a delta delta center tap. Phase A, C, and D, and they have to be in this order because B is called the bastard wild leg, literally. They call it the wild leg because the voltage between B and the neutral is what? 208. Remember we talked about that one for, you'll see a lot of, so we don't tie anything between phase A and a neutral. The only way you tie is between phase A and C and a neutral. It's the only way you do it. Where would you use a system like this, guys? Lift stations, city lift station, well houses. If we have a house and multiple wells in the house to pump the water, the city water, and all of them are 243 phase, and only a couple of lights and a couple of receptacles in that house, these. Very typically, they have 243 phase center tap. So what do you use the 124 for the receptacles and the lights? Very typical. Would you feed a commercial industrial building from this system? No. This is a unique system for special application. The reason, the main application for it, Brian, utilities love it all the time, is if it makes a lot of sense, only if 80% to 90% of your load is three phase and only 10% are single phase. Does that make sense? So the load, overall, your load, 90% of it is three phase motors.
Why use a 240 three-phase pump over a 480 three-phase pump?
Good point. Why can't we use, is there alternative for them? Yep, there is for 83 phase pumps. I don't know, a lot of cities that I've seen them at least are 240 systems. I think some of them come from Europe too. I think it has to do with Europe because they come from Europe and they're 220, but they're single phase though. I don't know, that's a good point. Why, there's a lot of them. I mean, well houses running at 243 phase. Why can't we run 208, for example, or 480 and call it a day? Good point. I guess it's whoever specified the material at the time. It's also cheaper. So here, take this. I know I can tell you one little thing, advantage of it. What's the alternative of not using 240? There are two alternatives. Alternative number one is 208. 208 is a lower voltage than 240. Lower voltage, more amps, right? More losses. So 208 is not a good voltage for a three-phase system, not the best voltage. Okay, so put it aside. 240 is better in three-phase than 208. What's the next alternative? 480. What happens if you have 480 system inside your pump? What do you need for your lights and receptacles? For receptacles, at least. You need a transformer, right? So yes, you're adding a transformer. So it's kind of a compromise between having 480, and then you have to have a transformer for your receptacles at least, because the lights you can burn them at 277. But the receptacles, we cannot burn our receptacles, convenient receptacles at 277. We don't use them. So that's kind of a compromise between 480 and 208. Okay, so that's the only way you can get it. Any questions about this? Yes, sir.
So if you were to connect the panel after the transformer, basically, if you wanted 240, you'd be connecting breakers from A and C, right?
This is how your panel will look like. You will have, I'm just going to say phase A, phase B, phase C. When you look your panel, this will be phase A, this will be this will be phase, just don't look at the color code, phase B, and this will be phase C, right? Okay, and then if I have a three-phase load, look how they do it. If we have a three-phase load, suppose I have a three-phase load, what they do, guys, you take one from here, and one from here, tie them together, and here's my three-phase load. Okay, makes sense?
Yeah.
One from every phase, right? Okay, one from every phase. That piece of cake, one from every phase. That's three-phase pump. If I have a single-phase load, suppose I have a single-phase load. Here's my neutral. I have to put my neutral here. Suppose I have a receptacle here, so I need a neutral. So what do you do for the receptacle? You take the receptacle to the neutral here, and you can feed it only from phase A, in this case phase A. So I come to A here, oops, take one and go. Or if I have another receptacle in this area here, I can the same thing, I can feed it from the neutral or from phase C.
And B is at 208.
B, I can't feed anything from B to neutral. So when you guys open the panel, you will see circuit breaker, space, circuit breaker. Because phase B, you can't use it. So if this is a delta, they call it delta 6 or 10 panel. If this is panel, when you're looking at this, you will see a circuit breaker here, space, nothing here, and another circuit breaker. Then circuit breaker, space, circuit breaker, space, circuit breaker. That space, you know what a space is, just a cover like this, exactly like this. This will indicate to you that that's phase B, you can't use it.
Unless you're doing a three-phase.
Unless you're doing three-phase or two-phase, or two phases. Like if here's the two-phase, do I have a two-phase here? I don't have two-phase. I can use two phases. For example, can I use A and B only? Just A and B to feed the load? Yes, A and B. But not B and neutral.
What voltage does A and B get?
A and B is 240 single phase.
Oh, I thought A and C was 240.
Both of them, all of them. Guys, from this system, you can feed the following. Okay. From this system, you can feed the following. You can feed 240 single phase. You can feed 240 three phase, or you can feed 120 single phase. Right? 243 phase, you just take three phases, A, B, and C, and feed it to the motor. Cool? Now, 240 single phase, you just take phase A and B, or B and C, or C and A. Any two. Not a big deal. That's okay.
Do you have to worry about unbalanced loads with that?
Yes. Then you have to balance your load. Like if you have 6 of them, you have to kind of stagger them between phase A, B, B, C, and CA. Okay? Good point. If I have a 120 load, the only option that I have two options, not a third option. Either I go from A to neutral or from C to neutral.
So any two-phase, 240 single phase, you always want to use the B, right? Balance.
Yes, balance your load.
But yeah, 208 volt single phase motor.
We can't use it.
Can you use that on phase B?
If you use it, it will run,
Yeah.
but it will screw up the system. You're not supposed to use it. Have you ever used that? Oh my God. Now, the good point, could I have used 208? Now I have 3 voltages. If you use it, would it run? It will. It will burn your transformer. It will unbalance your transformer. If you have a smaller load, 208, could I have run a smaller load 208? You will. Yeah, it will balance the windings.
Oh,
Yeah, it will. Certain windings will be overloaded. Let's just keep moving here because otherwise, could I have run it with a certain loads and calculate it? Yes. You're not supposed to based on the code. Okay, so I want to remind you guys, look at this phase A. The one here is 100, 100, 150. Anybody knows why this transformer is 150? Look what's tied to it. What's tied to it? The neutral. The one that has the neutral is always 50% bigger than the others. Typically, 50, 40% bigger than the other two. Everybody, they otherwise don't do with the system. Always, the one that has the neutral is fatter, bigger, slightly. Anybody knows why? What's the 50 here? 100, 100, 100. What's the 50 extra here? That's the neutral load. They call it the neutral load. Cool? That's it. Any questions, guys, before we go ahead and start it? So this transformer that feeds this section here is 50% bigger than any one transformer. And the reason for this, because it's going to see the 3-phase as well as the single phase. Let's go ahead and size. Okay, good. You'll see how we do it. Not derated. Okay. No, you're talking about derating open delta. I think you're confused between open delta. This is not an open delta. Is this an open delta? This is a closed delta center tap. There is C phase, but the transformer between C and B. The blanks is always B. In an open delta center tap, B. In an open delta only, you don't have single phase loads. It's all three phase. You know, it has to be open delta center tabbed, then it's B also. Okay, now take this KVA bank. There are two KVA banks in this case, guys. Good discussion. The first KVA is for the three phase. So the three phase, how many I have? Each one of them is going to contribute 100 plus 100 plus 100. Everybody understand why for the three phase, each one of them going to contribute 100. Why do you think I didn't put 150 here? Because if this guy is going to push 150, it will force this guy to push 150. What's going to happen to this guy? That's not rated for 150. It's going to burn. So when you rate them based on the other 50. You drop. So you rate them based on the two. So if this is 100 and this is 100, you only take 100 out of this. Okay. Three phase. You're going to see where it's going. So this will give me, so this will be 300 kVA. Okay, so that's my 300 kVA. Any question why 300, not the 150 is added here? The other 50 is going where? Right in here. Now the single phase kVA. Did you guys see the single phase kVA? Single phase kVA is what? The single phase kVA is actually you take the 150 that you did, subtract 50 out of it, subtract 100. Why do you think I subtract 100 out of that? Subtract 100, it's already used somewhere else, and that'll get me what? 50 kVA. That's it. Why? So I took the fattest, fluffiest transformer. I took 100 out of it. Why did I take 100? Because it already went up there. So the difference between the fattest transformer and the other transformers, one at a time, is actually the kVA. Everybody understand what the 50 kVA? And they call this is single phase kVA and neutral load. Neutral load. Why neutral load? Because that's just to tie phase A to the neutral. Just phase A to tie phase A to the neutral. Just to tie phase A to the neutral. So here's phase A, phase B, phase C. Then I can, and here's my neutral. Let's just put my neutral here. So now I have my neutral for a receptacle in here, and I can take it from here, take my neutral like we said here, and I'm going to take it from here and go to phase A. I'm not showing the circle. Well, let's show a quick record here. Or I can have another load here, and I have my neutral, same thing, go to the neutral, and to phase, which phase now? Phase C, not B. That's what we're talking about in terms of a neutral load. That's to feed you receptacles and lights if they're running at 120. Okay, that's where the 50 goes. Any question guys about the kVA three phase and kVA single phase? Now let's go size the rest. Okay, let's go to a V primary line. Very easy. This is a lot of these guys are straightforward now. V primary line. What's the primary voltage? Well, it's 2400 volt. Piece of cake. V primary coil. What's the primary coil? 2400. V secondary line. What's the secondary line voltage? It's a delta. What's the secondary line voltage? 240. Piece of cake. What's the secondary coil voltage? The secondary coil voltage. The secondary coil voltage is what? 120 volt. Actually, you should, the way we write it, it should be, there are two voltages. There is the 240 volt, and also there is the 120 volt, right? There is a coil that 240, and the coil that's split into 120. So these are the secondary coils, right? I will take you guys back here. This coil is 240. This coil is 240. This coil is 120. This coil is 120, right? So one coil, the 240 coil split in the middle. So the coil voltage, there are really two voltages for the coil on the secondary. One of them is 240 and one of them is 120.
The coil is still from A to B, isn't it?
Or from A to the neutral. If you look at it from A to B, it's this one, 240. If you look at it from A to the neutral, it's half of it. Okay, I primary three-phase. Now the voltage is a piece of cake, right? Voltages, did they go too fast over the voltages? The only one that I can see your point. If you're looking at it from A to A, it is 240, Chad. We just split it in the middle. But I'd like to throw the 120 to remind you that there is a voltage 120 that you can pull out of that point, right? So, but you can think, again, it's 240 center tap. That's why they call it center tap. All right, let's go to, now, I primary line three-phase and single-phase. Now we're going to start to split here, guys. Now we have two types of currents. We have a current that's three-phase current and a current that's single-phase current. That's why do we split it this way? Because there are neutral load and non-neutral load. Okay, so let's look at the three-phase. The three-phase is piece of cake, guys. Remember the three-phase bank that we did? How much the three-phase bank? It was 300 K divided by, what's the voltage on the, are we on the primary side, right? 1.73 times 2400. If you do this math, I came up with 72.3 amps. Anybody came up with something different? 72.3 amps. Right? Jerry, this is just the three-phase. We're not taking into consideration the single phase. Look at the single phase. Single phase is a piece of cake now. For the single phase, Aaron, what was the KVA for the single phase? The neutral load? 50. No, 50 by itself. 50 K divided by, okay, now 50 on the, we're on the primary. What was the coil on the primary? 240, 2400. Thank you. Do I multiply by 1.73 here? No, because that's a single phase, and that what you get, 21 amps. That's the only thing you do, right? So I have two line currents, guys. One of them is coming from the three-phase, and one of them is coming from a single-phase load. Okay? Now, phase A and C are going to see, that's when we start splitting here now, when we size phases. When we size phases. We're still on the primary. Yeah, we're still on the primary. Now, any question guys about how we calculate the primary current, line current on the primary side for phase, for three-phase and single phase, right? Now, thank you. Phase A and C, they're going to see both of them. Remember that? Because they're going to see neutral load. How about phase B? Only one. You got it. So for phase A and B, you take the 72.3 plus the 21, and that's how much they're going to see, these boys. 93.4 amps. 93.4 amps. That's how much they're going to see. 93.4 amps. Now phase B. Everybody knows why B is not going to see. What's B is going to see? B is going to see the following. It's going to see 72.3 plus what? Big fat 0. Why the 0? Is there anything connected between B and the neutral? No. So that plus 0, that will give you what? 72.3 amp. The reason why I put the plus 0, just to emphasize, there is no neutral load connected between B and a neutral. So here's the funny thing is, you're going to have three phases. Two of them are carrying more current than the other one. The question would be, Chad, is this an unbalanced system or not? Yes, it's an unbalanced system. But don't forget that that's why we have one transformer bigger than the other two. So that transformer that's bigger is going to push the extra current. So one transformer is going to work a little bit harder than the other two. That's all. Okay, and it's going to push them through phase A, push the extras through phase A and phase C, the lines, not B.
So is the primary, the three coils are the same size, aren't they?
Yeah, but that's on the secondary side. But on the primary side, it will be seen between these two phases. They will be taking from A and B on the secondary side, right? But whatever comes from the secondary first have to go through where? The primary, right? It has to go through the primary.
You don't have to make one of the coils bigger on the primary side if you're going to do that on the
Yes, yes. Here's the yes.
so there's going to be 150 bank kind of one
Primary, secondary. Yes, yes, yes. That here. Did I draw it? See that guy? That guy is primary coil here.
It's primary and secondary.
Yes, and secondary. Primary and secondary are big. Good point. Okay, so now that you guys got that one, that's really the hardest thing to digest is that there are two currents. A and C will have bigger current than B. That's all. Why bigger current? Because there's an extra 21 amp, extra 21 amp coming from the neutral current. Okay, now when we size the fuses and when we size the conductors, we have to take this into consideration. That's all done. You're going to take into consideration the size, so there will be two phases bigger size-wise, fuse and cable, than the other phase. And if you guys look at the utilities, they do it all the time. Okay, so let's go size number 7. Now we're going to go on the secondary side. Let's go on the secondary side. The secondary side, my friends, is no exception. The secondary side, we're going to have, let me use this color here. 300, the same thing, 300K divided, what's the 1.73 times, the three-phase voltage is 240, and that will get me a healthy 723, right? 723 amps, piece of cake. Now the neutral is only 50. Remember, it's only the 50, and the voltage, now, the neutral voltage, Aaron, is 120. But you're going to take half of the load, put it on one leg, and the other half is going to put it on what? The other leg. So that's why it will be seen as 240, because you balance the load between the two legs. So when you divide here, you don't divide by 120, you divide by 240. So you divide this by 240. This is the hardest to understand, because people say, well, Chad, it's 120. Why can't I divide by 120? Yep, because half of it is going to be 120 here, half of it the other one. So overall, it will be seen as a 240 system. So this gets you,
So you're still doing the entire length of the coil.
it will be seen as coming from the coils, the big coil that's split in the middle. So that will give you 208. 208. Did I do that right? Amp. 208 amp. Is it right? 50 divided by 2, is it 208? Do the math right? Okay. So that one is then should be, that's why it doesn't matter. This one should be 208 guys too, right? It should be 28. Can anybody does that? 50 divided by 24? No. Never mind. Yeah. Because you approximate it. That's what. Okay. Never mind. I'm just missing a 0. Never mind. We're good. 2.8. Yeah, because we rounded it. 2.8. Good. Okay. Now the same thing, gentlemen. The same thing. The A and C will see what? The voltage in A and C will be 723 plus. 723 plus what? 723 plus 208 equal, if you add these two babies together, We're at 931 amps. Though phase B is only going to see 723 plus big fat fluffy zero, and that will get you only 723 and not 33, Chad, and 23. The reason why I put the zero just to emphasize that it will be a zero. It will be a zero here. Losing my synchronization here. Okay. Wow. We are. There you go. Any question, guys? Any question? Cool. Now the challenge is we're going to go size the fuses. That's all. The rest is history. Not a biggie. We're just going to go size a fuse. Just going to do some synchronization here. Getting way out of whack here. Okay, so let's go and do this and do this. Okay, so now the next step, we do have a couple of transformation ratio that we're going to do. Okay, let's do the transformation ratio. Transformer ratio, guys. Number 8 transformer ratio is 2400 divided by 240, and that will give you 10. And my transformer is 10 to 1. That's based on coil, secondary coil to primary coil, the bigger coil, the big coil. Now, if you would take the 120, that will give you another transformer ratio between the phase and the neutral. But that's your transformer ratio. What's the transformation ratio? I didn't do the transformation ratio. Same thing. The transformation ratio, I did not do it, but it will be the same thing. Transformer and the transformation ratio will be the same thing. Okay, let's go directly into primary feeder. Sizing the primary feeder. Sizing the primary feeder, guys. The primary feeder. The first thing I want to, for A and see how we have two sizes now, one for A and C and one for B. Everybody knows why? So for A and C, what was the current for A and C was 93.4 for A and C, right? Now, we're going to assume it's continuous load, so I need somebody to help me. This is my amp. Then I will assume it's continuous load, so I'm going to take the 93.4, multiply this baby by what? 1.25. Can somebody, I don't have this one. Can somebody does the calculation for me, please? How much? 101.7 amp. Okay. And then I'm going to take 117 amp, take it to the same table. Remember that table? This one is going to be table 310.60C 77, right? Under 90-degree column. But remember, this time we're going to go, because the voltage is 2400, which side are we going to go under? Actually, I have it here. We did it, if we go back all the way, the other side, right here. Oops, no, not here, Chad. Right here. Now, instead of going to this side, we're going to go, guys, to this side, because the voltage was 2400 volt. Okay, and what was the current 117? 117, so we're here, 117, that will give me number 2. Am I right here? Number 2, right? 117 was 110. I'm going to go all the way to number 2. Everybody can see that? Why did I go to this column this time? Because I have 2400. Okay, number 2. All the way to number 2. All the way to number 2. Okay. Where was I here? Here. So that will be, in this case, let's see, that will be how many conductors? 3 conductors. What size? Three conductors, number 2 AWG. What's the medium voltage dash 90?
Why is it three conductors since it's only A and C phase? Because of the neutral?
Thank you. It's actually, thank you. You're right. We're doing only two. Duh, Chad. Two conductors. Very good point, because we're doing only phase A and phase B. Phase A and phase C. Okay, so let's do the same calculation, guys, for phase B. Running out of time, area here. Phase B. For phase B, it was set only. It's going to be seeing only the 72, right? For phase B, we're only going to do. Oh my goodness, split this one so I don't get confused here. 72 amps. Anybody knows why 72, not 93.4? Because it's only going to see the three phase. So do me a math, do me a favor. Take the 1.25, multiply it by 72. Can somebody give me the answer, please? 94. Thank you.
90.4.
90.4, but it's just basically 90.
90.4. Okay, 90.4 amps. And then, can you guys do me a favor and go all the way to the table? Take the 90.4 amps, take it to the same table that we did, and this will be one conductor. What size? How much? Number 4. Any second? Same table. Number 4, AWG MV-90 degree. One conductor. So, Jamie, can you see that one of them, two of them are going to be number 2 and one's going to be number 4. So when you look at the transformer, guys, you're going to see literally two of them bigger, thicker than the third one. And that's okay. Not a big deal. That's okay. Shall we do the primary? The secondary when you guys have a chance? The same table. I did not emphasize here it's going to be the same table, right? Same table. Almost done. All right, let's do the secondary, guys. The secondary, I'm going to have, just make room here for the secondary. So the secondary side, any question about the primary? So two phases are different than the third one. The secondary side, guys, I have at 931. Is that what we came up with, 931? So I have 931 amps, right? Then what do I need to do with it? I take 1.25 times 931. 931, right? What would that give me? I don't have that. Can you? 1,164 amps. Okay. Then now I need to parallel. Now I need to. This is for phase A and phase B. So so we have 10. How many sets I'm going to parallel? Okay. So now I'm going to go, because these are big, guys. 1, 1, 6, 4. I decided to use 3. Can you guys do me a favor? I decided to pull 3. Can you give me what's divided by 3? 388 amps. 388 amps, right? Okay. 388 amps. Now then, I'm going to take the 388 amps, take them to table 310.15 B16 under 75 degree column. What would that give me? 600? What would that give me?
600.
600. How many? Okay, this is how we're going to write it. Yeah, this is how we're going to write it. 3 sets of 2 conductors. Each one of them is 600 kcm. Let's assume it's THH. It could be though any insulation almost. THH. That rated for 90 degree or 75 degree. Why did I parallel here? Because I don't think there is no conductor that can give you a lot in 100 kcm. You have to go to bus duct almost. Right? What's the largest they can get amp wise? 600. No, not 605, something like this. 665 is the largest. So you can't, even if you want to, you can't pull it. Okay, phase B. I'm going to give myself room. You guys have room, so can do phase B. phase B. Now for phase B, I want to remind you, my friend, for phase B, it's only going to see the 723, right? It's only going to see for phase B 723 amps, right? Because the neutral is not on phase B. So do me a favor, any one of you guys, 1.25, same thing, multiply it by 723, will ya? What do you get?
904.
904 second, thank you, sir. 904. Now, I paralleled. Now, here's what you're gonna do. Now remember, how many sets did I run A and C? 3 sets. Could I run these two sets? I can. But if you do it this way, then you have to put them in different conduits. Typically, we put the 3 phases in the same conduit, guys. You have to if it's metallic conduits. Otherwise, you have induction heat. So since we're going to be putting them in the same conduit, the 3 phases, so you're almost forced to do what? Parallel 3. Almost forced to parallel 3. So let's take this one, long story short, and 904 divided by 3. What would that give you, Aaron? 301? 301 amps. And the last thing, if you take this one, 301 amp, take it to 310.15 B16 table under 75-degree column. Can somebody get me the answer for that one? That will be the following, right? It's going to be 3 sets of how many conductors? Of 1 conductor. Oh, now 3 sets of 1 conductor. What size? 500?
350.
350 can give you that? Oh, 350. 350 kcm THHN. I apologize for putting it way at the end. It's the 3 sets of 1 conductor, 350 kcm. That one for 10. I should have gone to the next one. I have room here. Okay. Any question, guys? Everybody can read that one. So 3 sets of 1 conductor, 350 kcm. THHN. Okay, let's go size and neutral, and we're almost done. Almost done. Almost done. So let's go to the neutral. I have my neutral. Now the neutral load, guys, we have now what was the current? Now for the neutral, the current that's going to be seen is only, what was the neutral current on the secondary 208? So it's going to be I don't like to say I neutral, but the current that we're going to be sizing as based in 208 amps. Now some of you might argue, say, Chad, there is no way on earth the neutral is going to see this. You know how much would you see this? You know how would you see this? If Jeff, if you went and you put all your neutral load on only A, how often that would happen? Only on A. You put all your neutral load on A, phase A, not C at all. You're going to see 208. So that's why I don't multiply by 208 or anything. Take that neutral. So highly unlikely you're going to even encounter that one. Since we're paralleling it, guys, I'm going to parallel it. Well, we have 208. Since I'm going to pull it with every phase, I'm going to go parallel. Well, I think it's a little bit overkilling here. Since we're paralleling, right? So I'm forced to parallel 3 sets. So divide this by 3. So let's just do that because we're paralleling for the phase. So that's my amp. Number 2, I need to parallel because I already decided to do that. I parallel 3. That will get me 69 amps.
You have multiplied by 1.25?
No, because the neutral load, it's highly unlikely, guys, highly unlikely that current will be all in the neutral. Remember, we're sizing a neutral. half of it is going to be in phase, this will be coming from phase A and phase B. The only way the neutral can see it, if you turn all phase A off, how often that would happen, and only phase B load is there. So highly unlikely, I wouldn't. You know, this is really even exaggerating. And even though if you take this one 69, so then because we paralleled 69, now remember when you parallel, you're going to take 69 amps. Take it. Can anybody size it for me? 310.15 B16 under 75-degree column because it's a three-phase system. What size under 75? So that will be number 4. Number 3 under 75. One conductor, number 3 or 4?
Number 4.
Number 4. Okay. Number 4, AWG THHN. But there's one little problem. Am I paralleling? Yes. Can you parallel less than number 1 odd? You can't parallel less than number 1 odd. So this will be 3 sets, of course, 3 sets. This should be your answer. But the problem is, because I'm paralleling, guys, you can't use this because of paralleling. So you have to go to 3 sets of 1 conductor. Each of them is 1 odd AWG. Why? Because of paralleling. Because of paralleling. Right? We're paralleling it. If we were not paralleling, we're done. But we're paralleling. We're putting them in different. You can't parallel this and 1 odd. The code says you cannot parallel this and 1 odd. Let's go to the fuse. So this would be my answer. Because if we were not paralleling, then it would be 4, number 4. Now, would it be wrong if I multiply by 1.25? No, but knowing that's a neutral load, guys. Yeah, I mean, we already saw, yeah, we already went higher anyway. See how sometimes, okay, so here's how the sizes would be, guys. So we have 3 sets. What was the first size that we came up with? Can anybody remind me, please? A and B, what was the size? 600? It was 600 kcm. And what was B size? What was B size? The conductor for B. My sizes are 350. Okay, so that will be 350 kcm. And what was my neutral size? 1 odd. Okay, so now you're going to have your neutral running with these conductors because you have to run a neutral with every load. Neutral with every load. So that's what the conduits are going to pull. Any comments, guys? Any questions? So that's my neutral. Let's go ahead into the primary fuses. Let's do fuses. Now we're almost done. Almost done. Hold your horses. For fuses, I will remind you for fuses, guys, we go to table 450.3 A or B? A. Why A? Thank you. Higher than 600 volt. Okay, so let's take the first A and B on the primary. So A and B, there was, first of all, there was 94 amps. Then you take the 94 amps, multiply these babies by what? By 3. That will get you, I think, 282 amps. And then you take the 282 amps, take it to 240.6, and you can, how many fuses? 2 fuses, and what size? 300 amp. Why? Because if it's not a standard, you can go where? You can go up. If it's not a standard, you can go up. Why 2 fuses though? Because that's fuse A and C. B, we're going to size B differently. Can you guys see how it's weird now? You look at a set of fuses, 2 of them are big and 1 of them is small. And that's okay. That's why this is kind of a weird. Okay, let's go to B. So that's my B. For B, guys, I will remind you that B is only going to see, B is going to only go and see to 73 amps. Only going to see 73 amps, right? Just the phase, the three phase. So take the 73 amps, multiply the same thing by 3. If you do that, you came up with 219 amp. And same way, you're going to take the 219 amp, take it to 240.6. That will get you how many fuses? One fuse, and the size of 225 amp. So you open the you open the cabinet, and you're going to see 2 fuses 300 and 1 fuse is 225, and you think, who the idiot did that? Be careful, because that's the system will be an indication that this system is actually an open a center tap delta. Center tap delta.
How come on this one for the primary went up instead of down?
Because this is high voltage side, coming from different table. Good point. If the one before it, immediately we came from 3B, different table. Yeah.
Because it's about 600.
Yeah, because it was 600. Remember, it was 480 on the primary side and 280 on the secondary. So both of them were less than 600, 600 less. You default to B, which tells you to go down. I know it's a lot. You just have to remember, guys, the 600 volt, higher than 600 volt. On the test, you get confused, let me know. Huh?
From reading it, it just seems like it says we're 125%. It's like only if it's 125% on the secondary side, you go up. Otherwise, if it's not 125% on the secondary side, you go down.
Yeah, but because it's the note number 1 is right next to the 125. Yeah, it talks about if you multiply by 150, you're not supposed to multiply by 150. So if you multiply by 125, which
it doesn't have the 125% on the top one, so it doesn't say it. So you would go down. It just automatically goes up.
okay, good point. Where does it tell me to go up or down? If it doesn't tell you to go up, what you must go where? Down.
So it's just not telling you to go up.
Yeah, this is the most confusing one, guys. Going up on a fuse is, they have to tell you which is safer. Safer is going down. Which is less safe to go up. Less safe, you have to have a permission. Safer, you don't have a permit. You don't need a permission to be safer. But less safe, you have to have a permission. So if you go up, you make the system less safe, you have to have a permission. A permission means a node. Very good point. Unless you want to custom design yourself a fuse, of course, at 282, or you set the circuit breaker if you have a circuit breaker. I think these are for fuses. Okay, let's go to the secondary, guys. Almost there. Almost there. The secondary side. On the secondary side, guys, the amps that we're supposed to deal with is 931 amps, right? That's what this is going to see. So you take the 931 amps, multiply this one by, what's my multiplier? 1.25, and that will get me a healthy 1164 amps, right?
Is it 125 or 250?
125. We're going to table 450.3b. On the secondary side, it says 125%, right? Secondary side. We're on the secondary. We move to secondary. Secondary side. Okay, then, my friends, you're going to take the 1164, take this baby to 24.6, and that will give me 2 fuses. Each one of them is, what's the standard? 1200 amp. I have 2 fuses. Each one of these fuses is 1200 amp. Okay, B. For B, guys, B is only going to see 723 amps. That's it, right? So let's do the same thing for B. you take 723 amps, multiply it by 1.25. That will get me a healthy 904 amps. 904 amps. Did I do my math right? 904 or 9? Okay. Then you take 904 amps, take this baby to 240.6, and that will get you a healthy, how many fuses? One fuse, 1000 amp. That'll give you one fuse, 1000 amp. One fuse, 1000 amp. Any question, guys? Any comments? Any questions? This is the last time we'll touch fuses and transformers. Start number one.
Let's start back.
Number one. Serious?
No.
Yeah. Any question, guys? Any comments? The last thing, Joe, my friend, you can't scratch your head, man. You scratch your head, you'll be picked on. Okay, short circuit. The short circuit, the last thing is a short circuit, guys. When you do the short circuit, you take, again, I shouldn't say secondary because that's a little bit confusing. I want to say here short circuit. Short circuit, piece of cake. Then you're going to take both the three-phase and the single-phase because that's the worst scenario, right? Three-phase and single-phase. So what's a three-phase and single-phase here? Add it together. That will give me 931 amp. That's your worst. Divide by the impedance of 0.03. Did I give you the impedance? It was. I give you the 3%, right? That will give you 31. Am I right? 31 kiloamp. Now, when you size your circuit breakers, they have to be rated for 35 kiloamp or 31 or higher, which is typically 35 or 35 in this case. That's it. So what we did, guys, we did delta Y transformers and delta Y center tab, delta delta. The last thing that left is to give you the homework when you guys are done with this.
You want that? That's up with the first one.
Homework. Two options. You type it, put it in the network, let me know, or you can write it and show it to me and I'll okay it for you. Cool? So last thing, homework. Here's what I would like you guys, homework number 2. We have a delta center tab, at 12,470 kV, 24120 on the secondary. The transformers are 200, 200, 300. Okay, 200, 200, 300. The impedance Z, my impedance is 4%, and you, my friends, are going to do these 16 things for your friend check. 14 things. Huh? Which one? 1247? Oh yeah, very common. Yep, 1247 is very common voltage. There's 13.8, 1247. Yep, very common. 1247, 2400, 1247, 13.8, 13.2. These are very common primary voltages. Any comments, guys? Any questions? Any comments? Any questions? The rest of the day, guys, we're going to work on the stuff. Tomorrow, guys, my expectation, please, is to hard copies of E1 through E14, load calculation done, and Microsoft project done, printed. E1 through E14, please make them 11 by 17. Everything else will be 8.5 by 11. Cool? Thank you, gentlemen.